Okay, in this video I'm going to build off of a previous video where I illustrated how to compute and make sense out of the sample covariance and the sample, basically the Pearson's R between two variables. So in that video I had a data set containing 40 cases or 40 individuals who had scores on a measure of self-efficacy and academic achievement. So person 1 in row 1 had a score of 19.85 on self-efficacy, a score of 26.71 on achievement. Person 2 had a score of 19.11 and 28.78 respectively on the two variables. So to carry out Pearson's R in SPSS, basically it's pretty straightforward. If you go to Analyze, Correlate, Bivariate, you can see that you have your two variables, self-efficacy and achievement. You just move those over to the variables box. And then you have to, and so by default, SPSS has Pearson's clicked. You also need to sort of be thinking about whether or not you want your test to be a one or two-tailed test concerning the correlation coefficient. And what I mean by that is that in addition to computing the correlation, you want to test whether or not you can reject the null hypothesis that the population correlation is equal to 0. So, when it comes to correlation, Pearson's correlation, the null hypothesis is that rho, which looks like a P here, but it's basically rho for x, y, which is basically reflecting the population correlation between x and y, is equal to 0, meaning that there is no relationship between the two variables in the population. If there's no relationship in the population, what that would mean is that if I had variable x and variable y, and I obtained population data on those two variables, what would happen is that as scores increase on x, there would be no systematic change in scores on y. So in other words, what you would end up with is a random display of points if you're plotting each person's score on variable x against variable y. So you'd have essentially a horizontal slope reflecting that relationship. So there's no relationship between the two variables. The alternative, there's actually a couple of possible alternative hypotheses. One alternative or research hypothesis is that rho for x, y is not equal to 0. Okay, so in other words, what would satisfy this condition is anything other than this non-relationship that you see right here. So in other words, you might have variable x and y, and you'd have a slope that looks like this versus x and y and a slope that looks like this. This is basically a positive relationship between your two variables. This is a negative relationship between your two variables. So in a nutshell, the research hypothesis would be supported, and you would reject the null if either of these two conditions are met. To test that out, you're actually utilizing the sampling distribution of t in order to test this out. So essentially, the sampling distribution of t, this is not a very good sampling distribution that's being drawn, but at the center of the sampling distribution lies the null hypothesis. Okay, so essentially this null is this up here. So rho is equal to 0. And essentially what you do is you are basically setting a criteria for rejection of the null. So in other words, if you observe a correlation that falls, in this case out in the region of rejection, either of the regions of rejection, then you would reject the null in favor of the alternative hypothesis. The region of rejection is defined by whether or not, or the regions of rejection in this case are defined by whether the null hypothesis is directional or non-directional. In this case, this is a non-directional hypothesis, so this is non-directional. hypothesis. So in other words, the regions of rejection would be located in the upper and lower tail. And in addition, there's also what's known as alpha, or your alpha level, and this is your criteria for rejection. So typically, researchers set alpha at 0.05. So in other words, if you obtain what is called a p-value that is less than or equal to 0.05, if that's your alpha threshold, then you would reject the null and you would conclude in favor of the alternative hypothesis. And I'll show you what that means shortly. So, so at any rate, this is one type of alternative or research hypothesis that you are pitting against the null hypothesis. There are also a couple of other alternative hypotheses. One is that rho for xy, so in other words, the population correlation between x and y is greater than 0. And so in order for you to reject the null hypothesis, then this is the general pattern that your data has to take on. If another possibility is that you could say, well, rho for xy is less than 0, in which case this is the type of pattern that you're looking for. So if this right here is your research hypothesis, then you would actually be testing in the upper tail of the sampling distribution. So you would use at your alpha level, you would set your region of rejection of the null hypothesis in the upper tail, and if your observed correlation within your sample data takes you out into the region of rejection in the upper tail, then you would reject the null hypothesis. By the same token, if you had this other hypothesis, which is rho is less than 0, then you'd be testing in the lower tail of the sampling distribution of t. And so if your sample data takes you out into this region of rejection, then you would reject the null hypothesis. So all this other area that you see right here in these distributions, this is the area called the region of non-rejection. So in other words, if you observe a sample correlation that puts you into these areas, then you would not reject the null hypothesis, and you would basically conclude that the population correlation is equal to 0. So that's sort of a quick and dirty description about how to test the significance of the correlation coefficient. So note that this particular research hypothesis is referred to as a non-directional hypothesis. And a non-directional hypothesis means that you will be conducting what is called a two-tailed test. So that is, and by default, SPSS gives you the significance level for a two-tailed test. If you're testing a directional hypothesis, which the direction is being reflected in the fact that you are putting your region of rejection into the upper or lower tail, then you would be testing using a one-tail criteria, in which case you would not leave the default on, but rather you would click on one-tailed in order to obtain the significance level for that particular test. So at any rate, I'm going to clear this out because it's a little confusing looking at everything at the same time. And let's just say that I am hypothesizing that there is just a relationship, not necessarily positive or negative, just that there's a relationship between self-efficacy and achievement. So I will click on OK. And so you can see that I have, this is what is called a correlation matrix. So you'll notice that the values in the upper triangle of the matrix and in the lower triangle of the matrix, those values will be equal. So at any rate, it's just the same correlation. So you have between self-efficacy and achievement, you have a correlation that's equal to 0.38. So that's not a particularly strong correlation. You might say it's a moderate correlation given Cohen's standards for judging effect size. But it is a positive relationship, meaning that as scores increase on self-efficacy, you also have increasing scores on achievement. You'll also notice that you have the significance level. This is basically referred to as a p-value. And essentially, you compare your p-value against the alpha level that you set. So like I said, the alpha level is your threshold. Basically, it's a threshold for committing a type 1 error, or your tolerance for committing a type 1 error. So researchers generally set that pretty low. Conventionally, it is 0.05. There are situations where you might choose to increase or decrease the alpha level, but the general rule is that if p is less than or equal to the alpha level that you set, I'll just say if, then you would reject the null hypothesis. So reject null. And essentially what that means is that you are inferring that from your sample data that the population correlation is not 0. Okay, so in this case, our sample R, so our correlation coefficient was 0.38, so Pearson's R was equal to 0.38. And so we are inferring, based on our significance test, that within the population the correlation is not 0, and that's basically reflecting the two-tailed nature of our test. Now, let's say we want to test a directional hypothesis, and logically you would expect that people who tend to score higher on self-efficacy would also tend to score higher on achievement. So in that case, what I would do is I would be testing using a one-tailed criteria. So in this case, I would say I would click on one-tailed, click on OK. And in this case right here, again, the correlation is exactly the same. And notice that the significance level, the p-value, is 0.008. So obviously, in this particular case, my research hypothesis was that rho for x, y is greater than 0. And in this case, if I look at my sampling distribution, here's where the null lies, which is rho is equal to 0. So what happened is that my correlation was 0.38, and essentially that takes me out into the upper tail of the sampling distribution, where basically the alpha level is set at this point. So this is alpha, and we see that our p-value was 0.008. So actually the p-value is being compared against the alpha level. So p was 0.008, and so you can see that the p-value was less than the alpha level that you set. We'd set alpha at 0.05. And so in this case, we would reject the null hypothesis and conclude that within the population, the correlation between the two variables is significantly greater than 0. Now, what if we had hypothesized the other? Let's just be really counterintuitive for the time being. And let's say, for instance, my hypothesis had been that the correlation within the population was less than 0. Well, you'll notice that still, basically the results would be exactly the same here. This is your sample. These are results based on your sample data. So if that were the case, you'll still have a situation where you'll see that, well, yeah, the p-value was less than 0.05. And you might think that you could reject the null in this case, but in reality you can't, because the direction of the relationship was positive and you had hypothesized a negative relationship. So in other words, if we go back and we look at our sampling distribution, of t here, the region of rejection would be in the lower tail of the sampling distribution. So your data, your observed correlation is putting you out here in the upper tail of the sampling distribution, and so you're looking for correlations that will put you out here in the lower tail, which is the region of rejection. So all of this area is the region of non-rejection. So region of non-rejection. So in this case right here, if I had hypothesized a negative relationship between self-efficacy and achievement, then I would essentially not be able to reject the null, and I would have to infer that within the population the correlation is 0. So that is basically sort of a brief introduction to null hypothesis testing using correlations. You'll note too, so I'll clear this out, you'll note too that when you look at the correlation matrix, the values in the primary diagonal are 1, and this is basically reflecting the correlation of a variable with itself. So in other words, 100% of the variation in the variable overlaps with itself. So you have achievement and achievement right here. So that's why you have a correlation that's equal to 1. So in other words, for those two correlations, if you have variable x and with a correlation with itself, obviously it's going to explain 100% of the variation and so you would end up with a correlation that's equal to 1. For the off-diagonal value, which we have right here at 0.38, what we have is we have variable x and we have variable y, and the overlap that you see right here, not well drawn of course, but that is reflecting the correlation between the two variables. So this is where the r value equals to 0.38 is occurring. If the relationship was stronger, then let's say if it was like a 0.7, then in that case right there you would expect that x and y would exhibit a lot more correlation between those two values. So at any rate, let's say this is 0.7. They would be sharing a lot more variation. So that's just kind of a brief introduction to looking at Pearson's correlation. Let me just kind of note too that if you want the covariance between the two variables, if you go back to correlate bivariate, we can actually go under options, and you'll notice that you can ask for descriptives, means and standard deviations if you want, and cross product deviations and covariances. So if you want the covariances between the variables, you can click on that, and by clicking on this, then you'll notice that you now have the covariances laid out. So here, the covariance, sample covariance between self-efficacy and achievement is 4.56. Now note that the covariance is printed out for the relationship between each variable and itself. So you'll notice that so you've got achievement and self-efficacy and self-efficacy. And basically the covariance on the primary diagonal, this is nothing more than the variance of the variable. So you can see, like for self-efficacy, the covariance of that variable with itself is 9, and basically, if you go up here, look at the descriptives for self-efficacy. If you take the square of the standard deviation for self-efficacy, which is the variance, that would actually give you the same value, which is 9, which is what you have right here. You can see right here for achievement, the covariance was 16. So if you were to go up here to the standard deviation and square this, which would get you the variance of that variable, that would also be 16. So when you look at the covariance matrix, the values on the primary diagonal, those are variances, and on the off diagonal, those are the covariances between your two variables. Now, briefly too, let's run a scatter plot and look at the relationship between the two variables. So I'm going to go up to Analyze, I'm going to go to Graphs, and you may not necessarily see it on here, but basically, let me just actually bring this down just a shade so you can actually see the what I'm talking about. So when we ran the original analysis, we were using Analyze, Correlate, Bivariate, and that's how we got there. If we were looking at scatterplot, we can go to Graphs, Legacy Dialogues, and then down to Scatter. Click on Simple Scatter, and then we just move our variable over to the x-axis, our achievement variable to the y-axis, and we can click on OK. And here we have our scatter plot reflecting the relationship between the two variables. If I want to look at the general trend in the data, seeing if there's a linear trend, obviously there's no apparent appearance of a nonlinear trend in this data. So I'm going to but I can double click on this, and if I click right here, it says Add Fit Line at Total. Then you can see by default it's going to set up a linear trend, and it's going to fit a straight line to that relationship. So now I'm going to click on Close, and then click this value, and now you can see this is the trend that is evident in the data. So let's look at one other. So this is basically a scatter plot where I've just basically added a fit line to it. Okay, so let's look at one other data set. This is a data set that has anxiety as an achievement. So basically you have 40 individuals who have a score on anxiety and a score on achievement. So in this case, I'm just going to model a negative relationship between the two variables. So to run the analysis, I just go to Analyze, Correlate, Bivariate. I just move these variables over. Again, if I was hypothesizing that just that there is a relationship and not necessarily a direction of the relationship, then I would leave the two-tailed significance test clicked. And so in this particular case right here, if I was doing this, then again, basically if I have my sampling distribution, the regions of rejection would be located in the upper and lower tails. Here's my null hypothesis, which is extremely poorly drawn, which is basically that there's zero relationship. So if my sample data, if my correlation that I observe in my sample takes me out in this region or this region out here, then I would reject the null. Reject. Null. So again, out in the tails, these are basically referred to as the region of rejection. So if my null hypothesis, if my alternative hypothesis was that rho for xy is not equal to 0, this is what is called a non-directional hypothesis, and what that implies is a two-tailed test. Note too that if what I observe in my sample data puts me within this area right here, this is the region of non-rejection, and so I would conclude in favor of the null hypothesis. So you can see right here, I'll just go ahead and run the analysis. I'm going to click this off, and so as you can see, we have a correlation between the two variables of -0.6. So there's a pretty strong negative relationship between our two variables. The p-value that you see right here, it says significance two-tailed. The p-value is actually, when people write in research reports, they will write, p is less than 0.001. And so as you can see, when you compare this value against the alpha level, which might be, let's say, if we use 0.05, you can see that we would be rejecting the null. But in research reports, researchers oftentimes will report using p less than 0.001 to report on the p-value. So in this case, we would be rejecting the null just by virtue of the fact that there appears to be a relationship in the population, given that our p-value is less than 0.001. if I was testing a directional hypothesis, which logically you would assume that greater levels of anxiety ought to be associated with lower levels of achievement, I would be clicking on the one-tailed test option and click on OK. And you can see that basically nothing really changed right here. The p-value was actually still less than 0.001. And so you would be rejecting the null. So again, if the research hypothesis had been that rho xy is less than 0, this is a directional hypothesis, and using our sampling distribution, we would be basically laying out our region of rejection in the lower tail. Again, here's our null hypothesis, and you can see that we have a negative 0.6, which is putting us out here in the lower tail, and so we're able to reject the null hypothesis. If, on the other hand, we had hypothesized that rho for xy is greater than 0, the region of rejection is still down here, but what that would mean is that let me take this off here. What that would mean, is that we would be testing, in the upper tail of this distribution, and the data would be located down here in this part of the sampling distribution, which would be the area of non-rejection. So even though the p-value that the computer printed out would be less than the alpha level, you wouldn't be able to reject the null in that particular case. So the computer doesn't care about what your original hypothesis is. It's going to give you a p-value, and if you're testing a directional hypothesis, you need to consider both the p-value and the direction of the relationship that's observed in your data relative to the directional hypothesis that you've laid out. So the last thing, we'll just kind of again look at the scatter plot. So in this case, we'll go to Graphs, Legacy, Dialogues, Scatter. We'll click on Simple Scatter. In this case, I'm going to move anxiety to the x-axis, achievement to the y. Click on OK. And so you can see that there's really a stronger trend that appears to be evident in the data, compared to this that we saw right here. So just to kind of make the trend more obvious, I'm going to click on Add Fit Line at Total, and you can see much stronger tightening up of the observations around the regression line relative to what we had seen right here, where there's a lot more dispersion of the observations around the regression line. So here you can see we have a negative relationship, and that's being reflected right here. So at any rate, that concludes this discussion on using SPSS and computing the Pearson's R and covariance and looking at scatterplots. So there you go.